Oh, wait, wrong show. Sorry. Good afternoon, everyone. Y'all don't sound sure about that. These comfy chairs are already starting to do their work. Settle in for a lovely lecture this afternoon. My name is Andrew Marsh. I'm the program officer for the University of Louisville's Leigh Ann Conn Prize for Renewable Energy. It gives me great pleasure to introduce Dr. Henry Snaith, the 2021 Leigh Ann Conn Prize Laureate. And if you're doing the math, that's 2023, right? So this funny little thing called COVID kind of delayed our visit, so we're really happy to have Henry with us. Henry is co-founder and chief scientific officer of Oxford PV and the Binks Professor of Renewable Energy in the Physics Department of the University of Oxford, UK. His multidisciplinary research work focuses on materials and devices for photovoltaic, solar energy conversion, and spans activities from new materials discovery and synthesis through device optimization to fundamental spectroscopic and theoretical investigations. He discovered that a new type of solar cell material, namely Perovskites, can produce extremely efficient solar cells when integrated into a simple thin film device, which are also very easy and cheap to manufacture. By combining Perovskites with silicon in so-called tandem cells, which he is going to explain, he has demonstrated efficiencies far beyond what is possible with existing commercial PV technologies, and promises to deliver the next generation of improved PV for powering the world toward net zero. Through his company, Oxford PV, Henry is pioneering the industrialization of this technology. As the technology scales to the gigawatt volume and beyond, it is anticipated to supersede today's technologies due to significantly increased power output and reduced cost of electricity produced. His work has been thoroughly recognized nationally and internationally. He was elected as a Fellow of the Royal Society of London at the age of 37 for starting a new field of research attracting both academic and industrial following. His awards and accolades include the Blavatnik Award for Young Scientist in 2018, being named one of Nature's 10 people who mattered in 2013, and he topped the rank of the world's most influential scientific minds from 2015 to 2017. He also received the Perovskite Prize in 2020 for outstanding merits in photovoltaics. Please join me in welcoming Dr. Henry Snaith.
Thank you very much, Andrew, for that extensive introduction. So I don't think I need to give a talk now. You've heard it all. And it's an absolute pleasure to be here. Massive honor to be the recipient of this prize this year. So thank very much to Hank Conn for creating the prize and for the selection committee through the process awarding it to me. Hopefully you won't be disappointed. So tonight or today, whatever time it is, I'm going to be talking to you about metal halide perovskites, and I'm going to really just talk you through our journey with perovskites from sort of this early scientific discoveries through to commercialization and industrialization. Before I do that, I'll just sort of put it into context. Now, the award comes from the Conn Center of Renewable Energy, so I probably don't need to preach this to most of you, but there is a global challenge of how do we curb our greenhouse emissions. And there's a whole load of trajectories of different scenarios and the sort of greenhouse gas emissions that could occur. And the current policies basically don't curb the greenhouse emissions enough. We've got a budget. We've only got about a third of our total carbon budget left if we want to limit global warming to less than 1.5 degrees. And that's becoming significantly more challenging as every year passes. But basically, we have to almost entirely, well, we have to entirely switch off carbon emissions by 2050 or have net zero, as in we're sequestering as much as we're generating. And to do that, we really need to make an absolutely rapid transition to renewable energy sources. So I'm going to talk to you about photovoltaics, solar energy, which is obviously one way of generating power in a clean and sustainable manner. There's a whole ecosystem around the renewable energy area. There's what do we do with the electricity we generate from solar? We also will want a fair amount of wind. It's a very good source of low-cost, clean power. And do we generate fuels? Do we store it in cars? We need to electrify industry. We can have cheap electricity. If we don't use it, we're not going to stop burning fuel, so we need to stop all the thermal processes. So there's a whole raft of activities required, and there's a lot of people here in Louisville and also all over the world working on all these different aspects. As far as photovoltaic solar energy is concerned, can we power the world with solar? We really need to aim for 100% power generation. That way we've got a chance of producing enough. To do that, it's a challenge, but it's not an insurmountable challenge. What I'm showing here is the graph. This graph is the deployed photovoltaic modules, the annual deployment or production per annum. 100 gigawatts means there's new solar panels going out that on a bright sunny day would produce 100 gigawatts of power. To put that into context, a typical coal-fired power station might be producing 2 gigawatts. So that's about 50 power stations on a bright day. Sun isn't shining all the time. But to get up to producing 100% power from solar, we need to produce a total of about 80 terawatts peak solar power, so 80 terawatts on a bright day. To do that, we only actually need to keep the industry growing at its current trajectory for just over a decade. So we've just got to enable the technology to keep scaling, keep driving it to be economically more viable for the next decade, and then actually if we stabilize the industry at somewhere between 3 and 10 terawatts per annum over a 25-year period, that will give us all the power we need. So the real key important time is now and the next decade or so, and that's where we've got to make the difference. So I'm going to now talk, well, specifically about photovoltaics. Sorry, forgot what the next slide was. I just want to tell you how a solar cell works. Some of you will know this off by heart, others may not. Solar cell is a semiconductor device. Semiconductors are materials that can either be insulating or conducting, and a solar cell becomes conductive when we shine light on it. And what we're doing is we're actually giving that light photon that carries energy, is giving its energy to an electron in the form of kinetic energy. So we're bombarding electrons, giving them kinetic energy. They can then conduct around inside the semiconductor, and they will flow out into the external circuit if we contact them with some metallic contact. As a physicist, we think of electrons and holes. So positive charge, the absence of electron, where the electron's been bombarded and it's gone, there's a hole left there, and we call that positive charge a hole, or p-type, and we call the electron negative or n-type. So I'm going to use the term p-type and n-type a little through this lecture. When I'm talking about p-type, it's about parts of the solar cell that conduct holes, and n-type is parts of the solar cell that conduct electrons. And basically, we take a slab of semiconductor and we contact it on either side with different materials that only allow the electrons, the negative charge, to flow in one way, and only allow the positive charge, the holes, to flow in the other. And that makes a solar cell. So what I'm going to do now, just to put some of the work I'm going to show you on perovskites into context, I'm just going to show a few slides of some of my early work in the areas that I started working in. So sorry, these slides have got a bit jumbled. I first started working on photovoltaics in about 2001, quite a while ago, more than 20 years ago. That's when I started my PhD. And there I was working on polymers, small molecules, plastics that can also conduct charge. And now I don't really need to explain to you, because a lot of you will have OLED screens. These are the same sort of materials that were being investigated for organic light-emitting diodes. You can actually also make solar cells with them. And the notion is that they're cheap and easy to make, and they should make inexpensive solar cells. But the problem is, if you just take a single slab of organic semiconductor, you can't generate charge in that material. You can absorb light, and it momentarily generates charge, but it doesn't live very long. That charge is lost. You lose that energy from the light very quickly, and you basically lose the energy. One way to overcome that is to blend two different materials together, two different polymers, one which conducts electrons, we might call it N-type, one that conducts the positive charge, P-type, and then when you blend them together, when you shine light, you separate the electrons and holes into different materials, and they can conduct out of these polymer layers. And that's so-called polymer blends, or it got termed bulk heterojunction. Hetero means different, junction is obviously a junction, and the bulk is because it's within the bulk of the active layer. So it's not a solid material, it's a blend of two different materials. After that, I started working on a technology that we call desensitized solar cells. These also follow the principle of needing to separate the positive and negative charges. Here we use TiO2 nanoparticles, titania. It's a pigment used in white paint. This material can conduct negative charge, electrons, and we can make a porous film of a few micrometers in thickness and actually then dye that, coat that with an organic dye. And in fact, the first recipient of the Leigh Ann Conn Prize was Professor Michael Gretzel, who was my supervisor at the time when I was doing my postdoc working on this stuff. So this made nice, colorful solar cells, and there's people trying to commercialize this for building integrated photovoltaics and areas where you might want colorful glass. Following this notion of needing this structure, this bulk heterojunction or this mesoporous structure from the titania, I did quite a lot of work with my group working on structuring oxides in a more controlled way. This is an example actually in collaboration with a colleague called Uli Wiesner from Cornell University, where we made a double gyroid template from block copolymers. These are self-assembled molecules that make this structured template. And then we could infiltrate it with a metal oxide precursor and form a porous double gyroid structured titania. We went another step further and actually made porous single crystals. So this is an example of a single crystal of titania, which is solid on one side and then porous on the other. We actually wanted it to all be porous. This was a crystal that didn't quite grow perfectly, but it illustrates it quite nicely. So the really interesting aspect of this material is you have single crystal-like electronic properties, but you have the high surface area you need from the porosity. So this was really exciting. I personally thought we found the perfect porous material. And this was in 2012, just before what I'm about to present you came along. So I'm going to now talk to you about perovskites. And before I do, I'll just start from a long time before I started working on them. This material was discovered in 1839. This is calcium titanate. It has this crystal structure that you can see there. But the materials that have proven very useful in solar cells are the tin and lead halide perovskites. They were also discovered a fair while before I started working on them, 1892. And in fact, there was quite a lot of work done by IBM here in the US, looking at these materials for semiconductor devices, light-emitting diodes, and also transistors for memory. For some reason, no one looked at them for solar cells at that time. So there was then not much activity happened until, I'll come back to that in a second, until 2009. And this is the first report of using these metal halide perovskites in a solar cell. And it was done by some colleagues from Towan University, Yokohama, Tom Miyasaka and his postdoc, Akiro Kojima. And there they took this porous TiO2, this porous TiO2, and instead of using a dye, they coated it in small little nanocrystals of this perovskite. And that was published in 2009. So that's quite interesting. The big issue with this cell that they made was that they used an electrolyte as the redox couple. This takes the positive charge or the holes off these perovskite crystals, and that same electrolyte actually dissolved the crystals. So they could put the cell together and measure it, but it literally lasted 10 seconds. So people didn't really follow it very much. I visited Towan University in 2009, just when this paper came out, and Tom Miyasaka gave a presentation then, and he showed this video, and I found this quite interesting. So this is a spin coater. In the research lab, we often make our cells by spin coating them on a chuck, and we deposit a solution on top. And this is a video of him depositing the Perovskite solution, and there's an ultraviolet light shining. So I'll play it. He deposits the solution. It's just a salt dissolved in a solvent. And as it spins, it suddenly starts glowing. And this is the Perovskite nanocrystals forming on the porous titania. And it's glowing, they're re-emitting light. And within that time, those crystals, that layer has already formed this interpenetrated network of glowing crystals. Now, at the same time, I was working with nanocrystals, but doing them with colloidal synthesis, and it took about 2 days to make about 25 milligrams of material. And this just took him about 20 seconds to get the same result. So I thought that was pretty interesting and wanted to start working on it. A few years later, or a year later, I sent a PhD student out. I managed to get a joint grant. And his task, Mike Leigh, was to learn how to make these perovskites and then come back to Oxford and try and make some solar cells with them. So this is our starting point for metal halide perovskites. Unfortunately, Kojima had stopped working on it by the time Mike Leigh went to Japan, but we managed to get the recipe off him, but we didn't get much instruction. And Mike, my student, was an electronic engineer. I'm a physicist, so he did make some mistakes with the chemistry early on, but we got there in the end. So our first Eureka moment was Mike came back to Oxford and made some solar cells with the titania, and then we swapped the titania for porous alumina. And alumina is an insulator, and we just wanted to test to see if we had some conduction through the perovskite as well. And he made 2 solar cells, and one of them was over 10% efficiency. Now you think 10% for a perovskite solar cell, that's pretty mediocre. At the time, our lab record was like 5.1%. So this basically over doubled our lab record. So it was pretty surprising this material worked. It was also surprising when we took out one of the key components that's meant to be conducting electrons, it actually got better. So that was a bit of a surprise. We published that paper and got quite an important paper for this stuff. And this really kicked off, in my view, kicked off the whole activity on perovskites. And this is just what I'm showing here is current voltage curves, current density against voltage. It's how we measure a solar cell, where power is obviously the product of current times voltage. The red curve is the alumina, but pushes out to higher power, current times voltage, than the one on TiO2. The next Eureka moment, which is it's sort of a logical progression, really. But when we were optimizing these devices, we had this porous alumina that was our scaffold. And we found that the devices got better and better and better as we made this alumina thinner and thinner and thinner. And it got to the point that we couldn't believe the perovskite was really going in this 50 nanometer thin porous alumina. So when doing some cross-sectional electron microscopy that I show here, what we found was the porous alumina, this bottom layer is the conductive oxide. This is a metallic but transparent metal oxide. We've then got the porous alumina, and then this layer is the perovskite. So what we found was the perovskite was filling this porous alumina, but then forming a solid continuous layer on top. And then this top thicker layer, this is our whole conductor material, our p-type charge extraction layer. So this was a surprise, because up until this point in time, I'd been living by the notion that we needed this interdigitated bulk heterojunction, porous structure, for any of these cheap and easy materials to work. And suddenly, we've got a solid absorber that is just processed and dried at 100 degrees centigrade and seems to be working better. So as we went thinner and thinner in the scaffold, the efficiency got better and better and better until at some point when it dropped down again. So we took it to the logical conclusion, got rid of the scaffold, and found that if we could optimize the growth of these thin films, we'd get really well-performing cells. So this is the structure, pretty much the structure of devices today now. We've got a conductive oxide. We've got a thin electron selective layer. You can barely see it in this electron microscopy image. It's very thin, just a few tens of nanometers in thickness. We've then got the perovskite absorber, then a p-type layer, and then a metal top contact. This device we call actually, I won't even go there. It's a solar cell. We can also flip them up the other way around, and they work quite well as well, actually slightly more stable. So why has everyone got quite surprised by this material? Why did it cause a bit of shock in the community? And it comes down to the fact that we could just coat these materials. They form semiconductor layers, and essentially their properties are pretty similar to 3,5 semiconductors. So 3,5 semiconductors, they're compounds using group 3, group 5 alloys like gallium arsenide, for instance. These are the very best semiconductors humankind can make. They're generally grown on really expensive tools via epitaxial growth, literally grow atomic layer at a time to get a perfect defect-free material. And what we find is we can dissolve these salts in a solution, spin coat the films, or just smear them over a substrate, and they've got properties very similar to these 3,5 semiconductors. So why can these materials be made so easily? Why are they have such a low defect density? And why do they work so well? And this has exemplified one of the things people try to do with really good quality semiconductors is see if you can get lasing from them. For lasing to occur, light amplified spontaneous emission, you need to populate the electrons in the conduction band, and you have something called population inversion, where you get such a high density that suddenly you get spontaneous emission. And that happens with these simply processed perovskites. If we just put them in an optical cavity, basically between two mirrors, you get this lasing line. It's characteristic of a very narrow line emission. So that was a surprise. And yeah, these materials basically form thin films very easily. They've got long carrier lifetimes and very low defect density. So moving on, we started, or at least the first perovskite discovered, or the first tin or lead halide perovskite discovered was cesium lead triiodide. That one works quite well as a solar cell, but there are some issues. Cesium is slightly too small for that compound to be stable in this three-dimensional perovskite structure that we want. So actually we want a slightly larger ion. If francium wasn't radioactive, we'd really like to use francium, but it's not going to be suitable for widespread deployment. So we actually have to go off the periodic table. We have to use organic cations. This is an organic ammonium cation called methylammonium. This was actually reported in 1978 as a material, methylammonium lead triiodide. And this is one of the materials that Miyasaka and Kojima used first in their first devices. And this was pretty much the material we started using. We put in a little bit of chlorine, but we basically started using this material. If we want to go further, we can use formamidinium. That's the next size up in ammonium cations, if you like. That works. So we first reported that in sort of 2013, 2014 of formamidinium lead triiodide. There are some advantages of formamidinium. It's slightly less volatile than methylammonium, and in fact, this seems really an important step forward for long-term stability of these devices. So, as well as using these single ions, we can also mix them. That can have improvements in stability. For instance, if we take formamidinium is actually slightly too large for the crystal, so cesium's a little bit too small, formamidinium's a little bit too large, methylammonium's a little bit too volatile, but if we mix formamidinium and cesium together at the right blend ratio, we can actually get something that works well, creates an ion that's the right size and is stable. And this is an example of what we call a mixed cation, mixed halide lead perovskite. And here, just to illustrate the improvement in stability, these films are held at 130 degrees in air, and over 6 hours these films don't discolor, whereas the ones including this more volatile methylammonium do. So that was an important step forward. The other thing that in the research field of perovskites, there's 1,001 additives people put into their films and devices. Some of these additives are put in for a rational reason. Others, there's an impression that someone's just been through the chemistry catalog and tried everything they possibly can. And probably most people's research is somewhere between those two approaches. This is an example, but additives can have a strangely positive impact. They can also have a strangely negative impact if you use the wrong additive. This is an example of a piperidinium salt that was added into a perovskite layer. This is some work that we did. And when we add this layer, this material in at just 0.3% with respect to the main perovskite material, so relatively low concentration, we get a nice improvement in efficiency, in voltage of the solar cell, and importantly, we also get a big improvement of stability. So these additives suppress some of the degradation processes that can happen in these devices. So one of the key challenges for perovskite solar cells is how do we make these materials fundamentally stable so they'll last for 25 years when deployed in the field? Because these are salts, they're crystallized salts. That's one of the reasons why they crystallize so well at low temperature, but it does mean they can be sensitive to things like atmospheric moisture. They can be more sensitive to temperature than silicon. So we need to tune the material and work out what additives we need to add and how they influence the stability. I mentioned that we can tune the composition. We can basically mix cesium, methylammonium, and formamidinium. We can mix the halides from iodide, bromide to chloride. And in doing that, we change the crystal lattice size. That changes the band gap. So we can tune the band gap, which is the band gap of a semiconductor is essentially the lowest energy photon you can absorb in the material to excite the electrons into this conductive state. And that governs, well, it governs what color they are and what color light they absorb. And this is really important for what I'll show you next, which is multi-junction cells. So a conventional solar cell is a single slab of semiconductor like silicon. But actually, if we just use silicon, we lose a lot of energy through thermalization. If we just use, we lose a lot of energy to heat as the sunlight's absorbed. Sunlight comes in a range of colors that you're used to looking at through a prism. Each color carries different energy. As a physicist, we like to think of photons not as their color, but as their energy, and we use a term called electron volts. That's analogous to voltage in an electrical current. So if a photon carries 1 electron volt, if you made that into a solar cell, you could generate, in principle, 1 volt of a potential difference. It's a bit less than that. There's some physics, again, that describes why that's a little bit less, which I'm not going to explain now. But if we take blue photons, they might carry 3 electron volts. So you could generate a solar cell with 3 volts. The red ones carry about 2 electron volts of energy, and out to the infrared it goes down. So the lowest energy photon absorbed by silicon, for instance, is about 1 electron volt of energy. So a silicon solar cell will never give you more than 1 volt in power. But if you stack solar cells on top of each other, you can get more of this electron volts of energy converted to electrical energy, so you can get higher voltage from the cells. For instance, if we put perovskite on top of silicon itself, we can fundamentally increase the efficiency. The absolute limit of efficiency for silicon is about 29% efficiency. We could pump that up to 45 at the thermodynamic limit, at the limit of what that could ever do. In a triple junction, that efficiency, so 3 on top of each other, that efficiency could go up to over 50%, towards 55% efficiency. In practice, we'll never quite get there, but they're the targets of what we want to do. So if we think about where silicon has gone, silicon is our main technology today, and there's a brick wall ceiling. The practical efficiency is about 26%. And to go beyond that, we need to go to these tandems and triple junctions, and this is where perovskites has a real potential to do it. So I'm going to now just show you a few things about multi-junction cells. Firstly, this is some calculations we did of the sort of efficiency we should target. These are the efficiencies we think we can practically get with today's perovskite cells if we tune their band gap, tune their composition to tune and make the different solar cells. So we should be able to make 2-junction tandems close to 34% efficiency, and 3-junction cells somewhere between sort of 36 to 39% efficiency. So these are the targets that we're aiming for. This is an example of a 2-junction all-perovskite cell. So we've got a wide bandgap perovskite on the bottom and narrow bandgap perovskite on the top. The record efficiency reported by Renshine Solar, that's a Chinese company, it's 29% for this type of solar cell. So they're pushing up there pretty quickly. What are the challenges? How do we get this up to 34%? We need to improve the voltage the wide bandgap cells generating, and we need to improve the stability of the low bandgap cell in this solar cell stack. So I'm going to show you a little bit on improving the voltage of the wide bandgap cell. This is a schematic diagram of the cell stack, all these different material layers. This one has the p-type, the positive contact on the bottom, negative contact on the top. What we need to do in this solar cell, the most of the losses occur between this absorber layer and these contacts. So the losses aren't in the absorber, but basically we have charge trapping at the interface between the absorber and these contacts. So we need to try to introduce some strategies to improve them. This is an example where we use a passivation layer. We do some treatment on top of the perovskite film as a second step to improve the quality of the interface between the perovskite and the N-type electron transport material. And there the voltage of these solar cells has now gone up to about 1.35 volts. So that's a really big step up in voltage. And these solar cells actually emit light pretty strongly. So because we've tuned the band gap to absorb visible light, you can now see the light that's emitted. So this is a solar cell where we don't shine light on it and get current out, but we drive current in and we get light out. And we can see it with our naked eye very clearly. And in fact, there's a whole analogous technology very similar to OLEDs of perovskite light-emitting diodes, where basically these device stacks are engineered slightly differently to emit light for displays. So the efficiency's storming up. There's a massive increase. This is an excerpt from the National Renewable Energy Laboratory's efficiency chart. And what we can see is the perovskite on silicon tandem cells are now up at 32.5% efficiency. So actually, we're going to have to revise our calculation. I think we're going to very rapidly get to 34 and have to reassess whether we can go any higher there. And the single junction perovskites, just a single layer, is already up very close to 26% efficiency. So power efficiency is there. So the key question is, can these devices be stable? How do we make them stable? Another question is, I've shown you that there's lead in the material. So one thing that people can be concerned about is, do we have to be concerned about the toxicity of lead? So of course we take this seriously, and we've looked at the environmental fate of lead in perovskite solar cells. But it turns out when you do a full life cycle assessment, the environmental impact of lead is extremely small. So as an example, we looked at the production of a perovskite on silicon tandem factory, and we looked at the ecotoxicity impact of lead in that whole process, and it amounted to 0.3% of the overall ecotoxicity of the manufacturing. And in fact, the silicon wafer itself amounted to 40%. So the heat and energy that goes into producing the silicon is actually far more, creates far more of a toxic effect than the lead in the solar cells. That's not to say that the silicon is toxic at all. In fact, it's very good. Compared to burning coal, it's orders of magnitude better. But the presence of lead has a very minor impact. And in fact, if it did leach into the soil, we found it gets sequestered by the soil very quickly, and we've done experiments to investigate that. So it won't then go forward into the water supply. So it's actually very safe to deploy. Once more, modules that are put out into the field will be laminated and encapsulated. And we did some tests by cracking some mini modules with hail, which is simulating something that may happen if there's a big hailstorm, and left these cells outside. This was done in Switzerland, to be rained on for 9 months. And we found that only 1% of the lead in the module actually came out over a 9-month period. So basically, the normal lamination and encapsulation pretty much seals all the material in there. So we shouldn't be concerned about the use of lead in these modules. And in fact, what we should be concerned about is sustainability. And there, lead is very sustainable. It's relatively abundant. It's sourced in high pockets. And we calculated how much of today's lead supply would we need if we wanted to produce 10 terawatts of perovskite modules. And it turns out it's about a day of today's annual supply. So, or at least it's just a little bit over a day. So basically less than 1% of our today's supply of lead every year would be required for modules if we wanted to produce all our electricity from perovskites. So there's not going to be a massive uptick in the mining and production of lead. It's already used en masse, and this would make a relatively minor impact to it. So for the last part of the lecture, I'm going to talk about industrialization and commercialization. I'm going to say quite a bit about Oxford PV. That's a company I spun out from my group in the university. But I'll also just highlight there's a number of other companies working in this area, targeting different aspects, different ways of deploying perovskites. For instance, Swift Solar is looking at flexible perovskites, tandems for high-performance lightweight applications. There's a Chinese company, Microquanta, that are making rigid single-junction perovskites on glass, really trying to go for low-cost power. And there's a whole range of others. There's also been many, many more to come, I would say. Lots of new startups. There was this Perovskite Prize here in the US. And in fact, at University of Louisville, I learned just a few moments ago that one of the winners, there were 3 or 4 winners from this prize. One of them is here from University of Louisville, which is a great achievement. And these are all companies looking for different aspects, applying different aspects to the perovskite ecosystem. So one of the key things alongside the scientific development, in order to industrialize this and translate it into real product, we've had to be mindful of capturing intellectual property. This was an assessment done in 2018 looking at all the top patent assignees for perovskites. Oxford Photovoltaics comes out as the top runner here, but there's lots of competition and lots of people filing. So we've been very active filing core early patents and also keeping the patent filings going over time. So in principle, to attract investment so that the investors who are driving the growth of the company and growth of the industrialization know that that product can be sold into the market because we've got enough protection over what we're doing. So in terms of Oxford Photovoltaics and the commercialization of this technology, we've got 2 sites, one in Oxford, just north of Oxford. This is where we do the research and development. So we take the innovations from the university group or that are occurring in the academic literature and turn them into, test them to see whether they're efficient and stable and whether they can be employed in a manufacturing environment. Materials and systems that pass the tests and look like they make a real improvement to the core product baseline can then get transferred over into our site in Brandenburg. This is where we have been running a pilot line since 2017 and have just ramped up a production line, which is going to be the first relatively small scale, up to 100 megawatt production line for these perovskite on silicon tandems. The cell technologies I just mentioned is perovskite on silicon, so we don't want to try and reinvent the wheel and go out with a thin film technology. In fact, we want to be able to process on silicon that's doing really well and advancing all the time with our perovskite layers and then produce something that is fundamentally more efficient. A key activity in the company, I mentioned stability. We've been working towards what is an international standard for solar. The IEC stands for International Electrotechnical Commission, and this is a standard that all PV, terrestrial PV modules and cells have to pass. We've been stressing the devices under different amounts of IEC tests. Everyone in the industry knows that the single IEC pass is an essential thing to have, but it doesn't mean the product will last for 25 years. And typically companies stress 3 to 5 times IEC. So that's what we've been working on in Oxford PV. For anyone who's actually in the field and interested in these sort of things, I'm showing efficiency against temperature here. This does bear relevance into how much power will we generate from the module while it's actually deployed. So when we measure the efficiency of a module, the standard temperature is 25 degrees centigrade, but actually on a sunny day, a module is never going to be at 25 degrees. It's always going to be hotter. And a fundamental thermodynamic, for thermodynamic reasons, solar cells lose efficiency as they heat up. It's part of the process. And there's something called temperature coefficient, which is how much efficiency do we lose per degree. A typical high-quality silicon module today will lose between 0.3 to 0.4% per degree. And actually, these tandem cells and modules lose much less, so only 0.2% per degree. So that means we're going to generate more power at high temperature, which actually means the energy yield which is ultimately what's important, is going to be pretty good. The company's also been very active. We do original work on small cells. This is what's done near Oxford. And then all the work in Brandenburg's been on full cells, trying to translate the efficiencies of the small cells across to the large cells. This is an example. Well, this is a video of the actual production facility. These are the silicon cells loading into the first line of the production tool. So it's showing some automation. Everything's done by robots and automatic handling. So this is a small factory for PV standards, but actually each cell, one cell's processed about every 1.5 seconds. So it's, as far as research is concerned, this is pretty quick. In my university lab, we have a tool that processes about 3 of these wafers a day. So this is certainly scaled up in rate and throughput. The cells are what the company's mainly focusing on. In fact, we're then partnering with module assemblers to take the silicon cell, process our perovskite cells, and then assemble it into modules. So part of that process has been getting high efficiency on these large cells. This here is a load of different current voltage curves. These are extracted from an efficiency record chart. At the time, this was, I think, from 2022. So last year, things moved quickly. This was the world record small cell, 1 centimeter squared. And this is the Oxford PV full area. I think this one was an M4 cell, which is at that time certified at just shy of 27%. So what you see here is the voltage is just the same. This shape of this curve is nice and square. That's a term we call fill factor. That's a really important thing for solar cells. That means it's got very few resistive losses. The current's a bit down. In fact, we know why the current's down. So this is something that will be improved on the large cells. What's really important is we can make full-scale modules that are giving over 400 watts per power, which is pretty efficient for a module of this size. So this is our target product. We're not quite there yet, but maybe by the end of the year, I'd like to say you'd be able to buy this, but they're already spoken for, the first ones. But certainly, once we get the full-scale production line up and running, these are the sort of things you'll be able to buy and put on your roof. And this is the starting point. This is where we begin. And there's all that headroom to get these cell efficiencies and module efficiencies up considerably over the next decade. I'm going to leave that, and I will finish by thanking my research group, who did a lot of the work I've presented, thanking Oxford PV, also a lot of collaborators, and thank you very much for your time. I'm happy to take any questions.
Okay. Hello? So because we're streaming, if you have a question, raise your hand. Let me come to you with a mic so that it goes out into the world. Anyone question for Dr. Snaith?
Thank you so much for a very enlightening speech. One question is, why lead? What's so special about lead?
So, I mean, the short answer is, I don't know. We don't know. It's a 2+ metal ion, and it's stable in the 2+ charge state, so it fits into that perovskite structure with iodide, with the halides. The orbitals are such that when you form that structure, you get effective bands. So in terms of the semiconductor physics of it, you've got nice curvature in the bands, you get low effective mass for the electrons. So that means they can accelerate fast, so you get quite high charge carrier mobilities. Tin, in principle, should be better. It would be better. It would be an improvement. It's a lighter ion. So another thing that moderates how fast charge conduct in a semiconductor is the phonons, the vibrations of the ions. And lead's pretty heavy, so actually you get a lot of phonon scattering of the carriers. When you go to tin, it's a little bit lighter. You get a higher charge carrier mobility. But tin has a very negative aspect that it's not so happy in the 2+ charge state. And in fact, it'll oxidize to the 4+ charge state, and then it comes out of the lattice. So we get lots of tin vacancies in the tin perovskite. We haven't managed to find other materials outside of that that work. We thought we were onto a winner. We were mixing bismuth that's 3+ with silver that's 1+, and at a 50-50 mix, you get what's called a vacancy-ordered double perovskite. That hasn't worked so well. There's fundamental reasons why charge get trapped with the presence of bismuth ion. We decided, well, if tin wants to go to tin 4+, let's make a compound with tin 4+. We can make something that's called a vacancy-ordered double perovskite, tin 4+. That's got very flat bands electronically, so very low mobility. It's not really a semiconductor. It's more of a dielectric. So if we look at the periodic table, there should be other elements we can find with halides, with these perovskite structures. We don't even know if the perovskite structure is essential. It's something that happens to accommodate a lot of different ions. So we've got this flexibility of tuning the composition, tuning the band gap. But as long as there's electron hole, the orbital overlap within a crystalline solid, you know, there are good semiconductors that aren't perovskites. Gallium arsenide doesn't form a perovskite structure. Cadmium telluride, another great photovoltaic material, isn't perovskite. So there will be prospects of finding other materials. But for the halides, it seems like the lead and tin are pretty much the only ones that work so far, and lead seems to be specifically good.
Sure. Hi. Oh, absolutely. Farshid Ramazani from chemistry department. So you mentioned that you actually had aluminum oxide there as an insulator, and then you got better performance. I wasn't quite sure what happened there.
Okay. So we were making solar cells that have a porous TiO2 anode, porous TiO2 electron transporting layer, and the perovskite infiltrates into that TiO2. So it coats the surface, absorbs light, but transfers electrons into the TiO2, and then they transport. We swapped the TiO2 for alumina because we had some indication we were also getting electron conduction in the perovskite, so we wanted to test it. So it's a porous alumina layer, and we infiltrate it with the perovskite. So the perovskite crystallizes within the porous layer. And it turns out that electrons can conduct through the perovskite right down to the bottom, where they're then contacting an N-type metal oxide. At the time, that was TiO2, but it wasn't porous. That's just planar or flat. So the electrons could conduct through the perovskite and then out into the external circuit through the TiO2. So they were bypassing the porous. It was just acting as a scaffold, the alumina. It's not a dense insulating layer, but it's certainly not conducting any charge. It's just there as a physical scaffold.
Thank you so much for the nice talk. Jacek Jasiński from the Center. I have a question about the degradation. We know that there are two factors which are important in degradation, environmental or external factors like moisture or air, but there are also internal factors. One is this ion mobility, which, so, but of course you are showing that your cells will have warranty for 25 years. So I think you are certain about the stability of your cells, but since this is an internal problem, how do you avoid it? Because encapsulation, of course, won't solve this problem.
So yeah, firstly, to answer your question, in terms of the external degradation, standard encapsulation methodologies that are used in the industry seem sufficient. So using glass lamination, specifically with butyl rubber edge sealant, which is the same stuff that's used in double glazing, for instance, that's a standard method for encapsulating thin film PV in the industry. Silicon cells generally don't have the edge sealant. They don't need it. So we'd have the edge sealant, so a bit of extra barrier there. In terms of the internal degradation, this is where a lot of engineering's gone on in terms of additives, in terms of choosing the right charge extraction layers, in terms of modifying the surfaces and interfaces. This all affects the internal degradation or stability. So you're right in saying that perovskites, you can have mobile ions. So some of these ions, you can have vacancies, you can have missing ions, and then that missing ion can move around. or you can have extra halide in there that can migrate quite quickly. So that's about controlling the crystallization. It's about adding certain additives that suppress these processes. And then it's also about making the contacts and interfaces very stable against any effect from migration of these ions. So it's not been an easy challenge, but it's something we've been working on for the last 10 years in both my university group and also in the company. And we're in a very good place at the moment.
Other questions? I actually have one for you, and then I'll get to Sundar here. So the physics and chemistry behind what you've come up with here is one of the fascinating aspects of moving these toward commercialization and industrialization output. What have been some of the largest hurdles that you've overcome in terms of translating this technology out of the university and into commercial space?
Yeah. So, I mean, initially, one of the biggest challenges is it costs a lot of money to scale this thing up. We've had to do a lot of industrial work. We have 2 sites. We have a production line. So raising venture capital funding for this has certainly been a challenge. There's been the environment for fundraising goes up and down as well with everything else going on in the world. So it can be challenging. You need to have some fortune that you don't need to raise money when the markets are not very susceptible to that. So that's definitely been a key challenge. The other challenges are, how do we make these things last for 25 years? How have we made these things? How have we made ourselves confident that they'll last for 25 years? And that's taken a lot of effort. And certainly there's been some head-scratching moments of like, how do we solve this? We definitely need to solve this if we want this to be a real product. So there's been a number of sort of technical challenges we've had to overcome in the process. And they've required lots of work and again, lots of effort, people power, trying to understand processes and degradations as well as just manipulating and engineering solutions.
Thank you.
Yeah, this is Sundar Atre. Henry, can you just talk a little bit about the path that you kind of made us take for granted about the academic life and the commercialization life going in tandem?
So do you want to understand how do I balance the academic life and the commercialization activity? Or manage it, yeah. So, I mean, first thing is, my university work is funded from government grants, it's state-funded research. We have to publish that work. It has to be disseminated because it's funded by the taxpayer. So with doing that, we make sure that if we come up with an innovation, we make sure we file a patent on that first. Then after filing the patent, we publish the work, so it's disseminated. And then that IP is dealt with by the University Technology Transfer Office. So that's at sort of arm's length. Any negotiation, commercial negotiations in terms of licensing that IP to Oxford PV is all done by the tech transfer officer rather than myself, because I'd obviously be conflicted in those discussions. In terms of balancing the time, there's some time I spend for the company, some time in the university group, actually understanding what the real key challenges are for the technology has helped me direct the academic research more effectively. So I'm not just doing, I don't have my team working on things that just might be interesting. I mean, there's a few things we do that we just do because we think might be interesting, but most of it's trying to solve real problems, trying to tackle real issues that could then have an improvement, lead to an improvement on the technology. I also focus the university group on work that I think will be the next generation of technology. So we do some work on the perovskite on silicon, but actually we've got a lot more work working on the triple junction cell. So we want to deliver the next improvements for the different perovskite absorbers we need to move up between beyond 34% up towards 40% efficiency.
Hi, Matthew Mulvihill, grad student at the Conn Center. Nice talk. really enjoyed it. Kind of off the topic of the perovskites a little bit, but you mentioned that the lead ions that leach from your cells can be sequestered in the soil. Just curious on how that happens.
Okay. Well, firstly, how did we assess that? Maybe you don't ask that. You're not asking that question. But we took sort of standard soil samples. I say we. This is a very royal we. This was some collaborators in Switzerland who work with us on a European project. So it's a European-funded project. We supplied the materials and devices, but they did the experiments because they have expertise in this. We take a soil sample, put it in a beaker, and dissolve the perovskite material or the salts, or we take a solar cell and dissolve it in slightly acidic water so we can get all the material off. And then we pour that into the sample, and then we measure the rate at which the lead comes out of the water. And what we find is within 2 hours, it's all come out of the water. Then we take the soil and look at trying to extract the lead back out of the soil. And we find that only under very extreme conditions can we get very much lead out of the soil. So it becomes absorbed to the soil. Soil is pretty complex. There's tons of compounds and ions in the soil, and the lead is complexing with ions in there. We did do a study, and I can't tell you off the top of my head exactly what complexes form, but we did look to see what mineral complexes form and how the lead is absorbed into the soil. So it's bound in there basically and can only be extracted under very extreme conditions.
Quick follow-up. So is there any concern for bioaccumulation then if it's strictly an absorption of the lead?
So the level, if you kept putting modules out in a solar farm, they kept completely leaking into the soil in front of the module, after about 10 leak events, you'd then be at the level where you would have some concern over the amount of lead in the soil. But even after, if a module completely leaked, and bear in mind, we've also done trials, and as I showed, and even over 9 months, only 1% of the lead comes out. So most won't come out. And we're looking at worst case scenario, if it all came out, you could still farm on that soil in front of you by sort of all laws, certainly in Europe and in the USA. So the soil itself should not be problematic, and there shouldn't be a risk of bioavailability. The other aspect is when a module breaks, it will only has any risk of leakage if it's broken. And when it does break, it'll stop working, and those modules will be replaced. And it doesn't have to be replaced instantaneously, because as we can see from our trials, the lead leaches out extremely slowly.
That UofL Conn Center. You mentioned that you're looking at multi-junction or multi-layer perovskites. Any thoughts of not using the silicon as a?
Yeah, absolutely. So, I mean, I mentioned on the life cycle analysis, the silicon contributes quite a lot to the negative environmental impact. There is some, if you manufacture anything, there's some negative environmental impact. It also takes most of the energy input in the polycrystalline silicon production. That has to be heated, as you know, at 1,800 degrees for about a day. And then you've got to make the ingots or grow the wafers. So there's a high energy input there. You overcome all that if you go to the thin film perovskite. The other aspect is actually the fundamental performance of the low gap perovskite. This one's made with a mixture of lead and tin. That has a higher efficiency potential because it's a direct band gap semiconductor. So one thing I didn't mention in the talk is silicon needs to be a few hundred micrometers in thickness to absorb all the light. And that's because it's what we call an indirect band gap semiconductor. I know you know all these things, but just for the audience. And that basically puts a limit on the performance. So other materials that absorb much more strongly, like perovskites, only need to be 1 micrometer in thickness, and fundamentally we can get a higher efficiency. So ultimately, all perovskite multi-junction has a high prospect of being more efficient than silicon, as well as being less environmentally negative, so higher, more sustainable. Now, will that happen? There will not be a widespread transition, in my view, within the next 20 years to all perovskite. And it's really in this decade is where perovskite on silicon get established. The next decade, between 2030 and 2040, is where they can potentially supersede single junction silicon. Then it's the following decade where the all thin film technology can come through. Of course, who can predict timelines? So it might all happen in 3 years. But.
In closing, I wonder if you might take a minute just to impart some words of inspiration to those who would follow in a path of trying to commercialize their innovations and those who might be in a position to help them.
Yep. So, I mean, all I would say there is that if you have an idea that you think has a commercial opportunity and you think you could make it effective, then you should go for it, basically. It's a big step. It's easy. We're in a very comfortable situation as academic scientists when we're doing our research. We know where we stand. It's comfortable. We publish papers, and the end result is some scientific dissemination to the community, which, of course, lots of great things can build from. Starting a company puts yourself on the line, in the sense. You're saying, OK, I'm going to make this happen. I'm going to try and make this work. And there's a risk there that you're making yourself vulnerable. But if you don't try, it's definitely not going to happen, or at least it won't happen with you. You won't have any involvement with it. And if you do fail, then that's OK. At least you tried. So if you think about, would you be happier not trying and not failing, or trying and failing? Well, I think trying and failing would be better than not trying, because then you definitely fail. Because you might try and succeed, and then that's really exciting.
Thank you very much. A big hand for Dr. Henry Snaith.
Thank you. Thank you very much.
And I would invite you all to APNA Cafe this evening.